Welcome to the deep dive.
Great to be here.
Today we're diving into a really crucial topic. It's one that's seen a radical shift in how we approach it.
Authentication and authorization.
Exactly. For Angular applications specifically, if you've ever, found yourself wondering how to genuinely protect your app's sensitive data, or maybe why some seemingly common practices just don't stand up to scrutiny,
Then this is for you.
this deep dive is definitely for you. Our mission really is to strip away the confusion, shine a light on some fundamentally flawed approaches.
And guide you toward the gold standard.
The gold standard for securing modern single-page applications, yeah.
It's a field that's, well, it's constantly evolving, isn't it?
Yeah.
And getting authentication and authorization right it's more than just a technical detail.
Oh, definitely.
It's about safeguarding user trust and, the integrity of your entire system. We're going to break down these complex security concepts into clear, actionable insights.
Okay, so let's kick things off by looking at what not to do. That seems like a good place to start.
The anti-patterns.
Right. Our sources lay out several anti-patterns that developers have historically used, and critically, why they're just, dangerous in today's web environment.
Makes sense. Where do we begin?
The first one you might encounter, it's an Angular app that tries to handle user credentials directly, and it relies on a fixed API key.
Okay.
So, picture this. A login page built right into your Angular app. Users type their username and password there.
Right, in the SPA.
Yeah. And the application itself then tries to validate those credentials against maybe some internal list it has.
Okay.
And then to secure its backend API, it also stores a static API key, maybe hard-coded, maybe just easily discoverable, right there within the Angular application itself.
Got it. So why is that bad?
Well, why is this a non-starter? The core issue, fundamentally, is that the browser, by its very nature, simply cannot be trusted with secrets.
Okay. Cannot be trusted.
Anything sent to the browser is remarkably easy to inspect and, manipulate. A user can literally press F12, open the dev tools, and find these secrets you thought were hidden.
Right, it's all client-side.
Exactly. And beyond that, you've got common web attacks like cross-site scripting, XSS, or cross-site request forgery, CSRF. They could easily expose any sensitive data stored or handled by the browser.
So even if you try to hide it.
Even trying to encrypt these secrets, it doesn't really solve the problem, because the key you'd need to decrypt them would also have to be accessible to the browser.
Rendering the encryption kind of pointless.
Pretty much.
Yeah.
And the downsides don't stop there. That API key, it's static. It rarely, if ever, changes.
Right. Set it and forget it, maybe.
Which means if an attacker gets their hands on it, they could have unlimited persistent access to your API.
Ouch.
Plus, because the API only ever sees this one generic static key, it has no real idea who the user is.
Right. No user context.
Which completely prevents you from implementing any kind of user-specific authorization rules.
Yeah, it sounds like a house of cards, doesn't it? What immediately comes to mind here is how often developers, maybe especially those newer to security, might stumble into this. They think they're simplifying things.
Right. Seems easier initially.
But the underlying truth is the browser sandbox environment, while it's great for many things, it's inherently open. Open to inspection when it comes to sensitive data. So if the browser can't be trusted with these critical pieces of information, where do they belong instead? That's the question.
Exactly. And that leads us straight into the second anti-pattern, which is admittedly a slight step up.
Okay.
It involves using an identity provider, an IDP, with something called the Resource Owner Password Credentials Flow, ROPC flow.
ROPC. Got it.
So in this scenario, your Angular app still presents a login page. But instead of validating credentials itself, it sends the username and password directly to a dedicated identity provider.
Okay, so it offloads the credential check.
Right. The IDP handles the verification. If it's successful, it sends an access token back to your SPA, your single-page app.
Back to the Angular app.
Yep. Which then uses this token for making its API calls.
So what's the improvement there? Seems a bit better.
Well, your Angular app isn't directly storing or managing user credentials anymore. That's a definite win.
Okay.
Also, unlike that static API key, the access token typically has a limited lifespan.
Right, shorter validity.
Which reduces the window of opportunity for attackers if it gets compromised. And if you're using OpenID Connect on top of this, the API can actually get some insight into who the user is.
How so?
Through a unique identifier embedded in that access token. It's usually called a subject ID claim or subclaim.
Okay, so some user identity reaches the API, but
the core vulnerability persists. That access token, a very important secret, right? It's still delivered directly to the browser.
Back to square one almost.
And the browser, as we've established, just isn't a safe vault for these high-value secrets. So this leaves the user's secret, or at least the token granting access on their behalf, exposed to a potentially vulnerable client-side application.
Vulnerable to XSS, CSRF, things like that.
Exactly. And beyond that fundamental flaw, this ROPC approach often limits your ability to use modern authentication features, like federating with other IDPs.
Like login with Google, maybe?
Yeah, that often doesn't work well here. The login workflow also gets kind of tightly coupled to your application's build.
Meaning changes require a redeploy?
Often, yes. And it typically restricts user authentication to just passwords. It often lacks built-in support for MFA, multi-factor authentication, or newer things like passkeys.
Right, so it's limiting in features, too.
Definitely. Which brings us to anti-pattern number 3. This one tries to address some of those shortcomings.
Okay, what's this one?
It involves using JavaScript libraries specifically designed for OpenID Connect, maybe using the implicit flow or the authorization code flow with PKCE, but still client-side.
OIDC libraries in the browser.
Correct. With this approach, your Angular app redirects the user to the IDP's login page.
Standard OIDC redirect.
Yep. Once the user successfully authenticates on the IDP's secure domain, the IDP redirects back to your Angular app and supplies the tokens, like the access token and maybe an identity token, directly in the callback URL, usually in the fragment part.
Okay, so the advantage there is?
The clear advantage. Users enter their credentials directly on the secure identity provider's page, not on your Angular application.
Right, so the app never sees the password. That's good.
That's a definite improvement for credential handling. However, you can probably guess.
Let me guess. The tokens still end up in the browser.
The fundamental flaw remains stubbornly present. The access token still ends up residing in the browser's memory or storage.
Doesn't matter if it's implicit or auth code with PKCE, if it's client-side.
It doesn't really matter which flow you use here. If the final step delivers the token to the browser, the token will always end up exposed client-side.
And this gets even worse with refresh tokens, right?
Oh, absolutely.
Yeah.
This vulnerability becomes even more critical when refresh tokens are involved, because if a refresh token is stolen from the browser,
it can be used to get new access tokens.
Exactly. Potentially granting perpetual access to resources until that refresh token is revoked or expires.
That's a crucial pattern we're seeing across all these anti-patterns. It really underscores the foundational problem. The browser environment, just by its design, isn't a secure vault for these high-value secrets.
It just isn't.
It raises a very practical challenge for developers, then. If we absolutely cannot trust the browser with these tokens, how do we securely get them to where they're needed, which is usually the backend API, right?
Precisely. And this is where the original server-side authorization code flow comes into play. Now, this flow was initially designed for traditional web applications.
Where the server renders the HTML?
Exactly. And its most vital purpose, its core design goal, is to ensure the access token never directly touches the browser.
Okay, so how does it manage that?
Instead of tokens, when the identity provider redirects back after a successful login, it sends back just a temporary code. Think of it as a one-time use voucher.
Just a random string.
Yep, just a random string. The browser's only job is to pass this code along to your server, your backend application.
Okay, so the code goes to the server, not the token.
Correct. Your server-side application then takes this code and uses it in what's called a back-channel request.
Back-channel meaning server to server.
Exactly. It's a direct server-to-server communication, completely invisible to the user's browser. In this secure back-channel, your server exchanges that temporary code for the actual tokens: the identity token, the access token, and the refresh token.
And what makes that exchange secure?
What makes it secure on the server side is that your server authenticates this token exchange request using a client secret.
The secret only the server knows.
Right. It's a highly sensitive piece of information stored only on the server, never exposed to the browser. Without that client secret, the temporary code is basically useless to anyone who might intercept it.
Got it. That makes sense.
Now, a common question arises, right? Could an Angular app just try to do this code exchange itself, directly from the browser?
Could it pretend to be the server?
You could attempt it. You could make your Angular app, grab that code from the redirect, and try to exchange it for tokens with the IDP.
But it needs the client secret.
Exactly. To do that securely, you'd still need that client secret, which, as we've discussed multiple times now, the browser simply cannot keep safe.
And if you just didn't use a client secret?
Well, you could configure the IDP to allow the exchange without a secret for public clients, but then any stolen code becomes instantly usable by an attacker. There's no protection. Our sources are very clear on this. No matter what you do, there is simply no secure way to execute this token exchange directly from a single-page application like Angular, not without introducing significant vulnerabilities.
Okay. It becomes undeniable then. If secrets absolutely cannot live safely in the browser,
They need a secure home.
they must reside on a server. And this recognition, this unavoidable conclusion, is precisely what led to the widespread adoption of the Backend For Frontend pattern, the BFF.
The BFF pattern.
In fact, it's so important that from the OFUF 2.1 specification onwards, the old implicit flow is basically removed completely. It's deprecated, not recommended.
Right.
And using the BFF pattern has become the official recommendation for securing single-page applications.
Now, I know what some of you might be thinking out there. Hang on, I'm a front-end developer. I don't want the hassle of building and maintaining a backend just for authentication.
It's a common reaction.
And it's a completely fair thought. But our sources, and really the security community consensus, are unequivocal on this. Unfortunately, there's currently no other fundamentally secure way to play this. It's a necessary security boundary.
You need that server-side component.
You really do. So with the BFF pattern, what happens is your Angular application gets its own dedicated backend. This is your BFF.
Backend For Frontend.
Exactly. And it serves a singular purpose, really. Handling all the complexities around authentication and authorization, and crucially, securely managing those secrets.
Okay, so how does it work in practice?
When your Angular application needs to authenticate a user, say, they click a login button. It doesn't do anything complicated. It simply sends a request to a designated endpoint on your BFF. Maybe something like bflogin.
Just a simple request to its own backend.
Right. At this point, the BFF takes over completely. Now, in a very basic setup, the BFF could handle the login itself, maybe with its own form, and set a session cookie.
Okay, but that's not the preferred way.
No, the recommended and far more secure method is for the BFF to act as a client to an external dedicated authentication provider, an IDP.
So the BFF becomes the OAuth client.
Precisely. The BFF initiates the authentication process using the standard secure authorization code flow. The user then gets redirected, usually, to the identity provider's login page. They securely enter their credentials there.
On the IDP's trusted domain?
Yep. Upon successful login, the IDP sends that temporary code back to the user's browser in the redirect. But here's the crucial part.
The BFF intercepts it. Or gets it somehow.
The browser sends that code back to the BFF's callback endpoint. And it's the BFF that then performs the secure server-to-server backchannel request to the IDP.
The backchannel exchange.
Right. To exchange that temporary code for the actual tokens, access token, refresh token, identity token. This critical exchange never leaves your secure server environment. It's completely invisible to the browser.
Okay, tokens land safely on the BFF. Then what?
Once those tokens arrive safely at the BFF, it validates the identity token to confirm the user's identity. Then it sets a session cookie in the user's browser.
A session cookie, like traditional web apps.
Exactly. But this cookie is quite special. It can contain user-specific claims, maybe extracted from the identity token. The BFF can even add its own extra contextual information if needed.
What happens to the original tokens?
The identity token itself is typically discarded by the BFF after validation. But the access and refresh tokens, they're either securely held by the BFF itself on the server,
Server-side session storage, maybe?
or they can be securely added to that session cookie, but only after being encrypted.
Encrypted in the cookie?
Yes. And the key for decrypting this cookie is known only to the BFF. That makes its contents completely useless to anyone else, even if they somehow got the cookie.
Right. Without the key, it's just gibberish.
Plus, this session cookie is flagged as HTTP only.
The HTTP only flag. Important.
Very important. It means JavaScript running in the browser cannot access it.
Oh.
This provides a really strong defense against cross-site scripting or XSS attacks where malicious scripts might try to steal cookies.
That's the real genius of the BFF pattern, isn't it? It effectively creates this secure bridge. The untrustworthy browser sends a simple message, basically, to the trustworthy BFF.
Yeah, log me in, or here's a code.
Which then handles all the sensitive negotiations, the token exchange, the secret storage, completely shielded from potential client-side compromises.
And yet, from the user's perspective,
It's seamless. The login just works. This is the fundamental shift, the best practice for secure SPA architecture now.
so beyond just login, A robust BFF usually needs a few other key endpoints to manage that user session.
Makes sense.
Like logout. Exactly. First, there's a logout endpoint. When your Angular app calls this endpoint on the BFF does a couple things. It deletes its own session cookie, obviously.
Breaks the session.
But if you're using OpenID Connect with an external IDP, it can also redirect the user to the IDP's official end session endpoint.
To kill the IDP session too.
Right. This ensures that the IDP's single sign-on cookie is also cleared, which effectively logs the user out across all applications that might be sharing that same IDP session. It can even trigger things like front-end or back-channel logout notifications to other connected apps.
Comprehensive logout. Good. What else?
Then there's often a user endpoint, commonly something like the fuser. Remember, that session cookie is HTTP only and encrypted.
So the Angular app can't read it directly?
Correct. It can't get the user's details or even know if they're logged in just by looking at the cookie. So instead, the Angular app makes a simple HTTP request to this diffuser endpoint.
And the BFF checks the cookie.
Yep. The BFF receives the request, checks for a valid session cookie, decrypts it if necessary, and then returns the user's claims or simply their authentication status.
And if there's no valid cookie?
If there's no valid session, the BFF responds with a 401 unauthorized status. That's the signal to your SPA that the user isn't currently authenticated.
Okay. Clear way for the SPA to know the state.
Then what about accessing APIs? What if your Angular app needs to talk to an external API? Maybe one that's shared by many other applications and expects an access token.
Right. The Angular app doesn't have the access token. The BFF does.
Exactly. So the BFF acts as a proxy, provides dedicated endpoints, maybe everything starting with API, for instance. When the Angular app calls API some resource, the request goes to the BFF. The BFF then forwards that request onto the actual external API.
It adds the token.
Crucially, yes.
Yeah.
The BFF automatically attaches the necessary access token, which it holds securely, before forwarding the request.
Neat. A secure gateway.
Exactly. And finally, you can also define API endpoints directly within the BFF itself.
APIs hosted on the BFF.
Yeah, these endpoints are designed exclusively for your specific Angular application. And importantly, they require a valid session cookie for authentication, not an access token.
So they're protected by the session, just like the diffuser endpoint.
Precisely. And for all these session-based endpoints, that session cookie absolutely needs to be a same-site cookie.
Right. Let's talk about same-site. You mentioned it's critical.
It is. It's a critical component for protecting against cross-site request forgery. CSRF.
CSRF, yeah. Nasty attack.
What same-site means, essentially, is that the browser will only include the cookie in requests that originated from the exact same site, the same domain, that originally set the cookie.
So if evil.com tries to make my browser send a request to mybank.com,
the browser won't include the mybank.com session cookie if it's marked same site. It acts as a powerful barrier against malicious websites tricking a user's browser into sending authenticated requests without their knowledge.
Okay, but you mentioned a challenge.
Here's the potential snag. If your BFF, your backend, and your Angular application are deployed on different domains, say api.myapp.com and app.myapp.com, the browser sees them as different sites.
Even if they're subdomains.
Even subdomains, often. So when your Angular app at app.myapp.com tries to make a request to the BFF at api.myapp.com, the browser won't send that crucial same-site cookie.
Which breaks the authentication.
And opens up potential attack vectors. The solution, in principle, is simple. You need to ensure they operate on the same site from the browser's perspective.
How do you achieve that?
Well, one way is for the BFF itself to directly host and serve the Angular application static files. Serve the index.html, the JavaScript bundles, everything.
Okay, possible, but maybe inconvenient.
Often, yes. Especially if your front-end and back-end teams have separate development workflows and deployment pipelines. The more flexible and usually more practical solution is to use a web server acting as a reverse proxy.
Like Nginx or Apache.
Exactly. Or URP in .NET or others. This proxy sits in front of both your Angular app deployment and your BFF deployment.
Good.
From the browser's perspective, everything appears to be running on the same domain, maybe just myapp.com. The proxy then intelligently routes incoming requests.
How does it know where to send things?
You configure it. Maybe requests starting with myapp or API go to your BFF service, and all of the requests go to the service hosting your Angular SPA's static files.
So the browser only ever talks to myapp.com, and the proxy sorts it out behind the scenes.
Precisely. And because all requests are going to myapp.com, the browser happily sends the same site cookie along with requests to the BFF endpoints. Problem solved.
Clever.
It's also worth noting same-site cookies have different modes. There's lax, which is often the default in many frameworks now. It makes a limited exception, allowing the cookie on top-level navigations using GET requests from other sites.
Okay.
But there's also strict. For maximum security, it's generally best practice to configure your same-site cookies to strict mode whenever you can.
What does strict do?
It eliminates all cross-site exceptions. The cookie is only sent if the request originates from the exact same site. It tightens your defense even further.
It's really fascinating how a seemingly small detail, like a cookie flag, the same site attribute, when you combine it with architectural patterns like the reverse proxy, it creates such a robust defense against a common and really dangerous attack like CSRF.
Wow.
It effectively patches a critical security hole that many older or, frankly, less secure authentication patterns just leave wide open.
Absolutely. So to make this a bit more concrete, less abstract, our sources walk through an example. They use ASP.NET Core for the BFF, but remember, these are universal concepts. They apply whatever back-end platform you choose, Node.js, Python, Java, whatever.
The principles are the same.
Right. In an initial sort of basic demo setup, you'd start your BFF project. It's typically configured maybe using something like map fallback to file in ASP.NET to automatically serve the Angular application.
Ensuring they run on the same site.
Exactly, from the browser's perspective. So you, the user, you click a login button in the Angular app. The BFF intercepts this, maybe redirects to its own basic login page account login, hosted by the BFF itself in this basic case. Yep. You enter credentials. The example uses Bob. The BFF checks these credentials, maybe against a hard-coded list for the demo, establishes an authenticated session, and sets that secure session cookie.
The HTTP only, same site strict, maybe encrypted cookie.
Ideally, yes. Then the BFF redirects you back to the Angular SPA.
Okay, back to the front end.
At this point, your Angular app knows to check if there's a valid session. It makes that request to the BFF's user endpoint, BigUser. The BFF receives the request, sees the valid session cookie, decrypts it, and returns Bob's user claims.
And the SPA knows Bob is logged in.
Right. The Angular app can then use this session to confidently call other API endpoints on the BFF, maybe API houses, to fetch some data. The session cookie is automatically attached by the browser to these requests. You might see user claims like, "Welcome, Bob," displayed on the screen, rendered by Angular using the data it got from the BFF's user endpoint.
Okay. And logout.
When you decide to log out, the Angular app simply calls the BFF's logout endpoint, maybe bflogout. The BFF deletes its session cookie and redirects you back to the SPA.
And the SPA checks again?
Yep, the SPA checks the BFuser endpoint again, but this time the BFF sees no valid cookie and returns a 401 unauthorized status.
And the SPA updates the UI to show the logged out state?
Exactly. Back to the anonymous view.
This initial example, even though it's basic, it perfectly illustrates that core principle, doesn't it? The BFF completely encapsulates the authentication logic and all the secret management.
Yeah, it owns it.
The Angular application, it doesn't need to know how any of that authentication works. It just needs to know which BFF endpoints to call for login, logout, and user info.
That's it.
The separation of concerns is just fundamental. For security, obviously, but also for maintainability. It keeps the front end clean.
Definitely. So let's zoom in a bit on the Angular side of this picture. What's going on inside the SPA?
Okay.
The heart of the authentication handling in your Angular application would typically live within an auth service, a dedicated service.
Makes sense. Centralize it.
This service might maintain some internal reactive state, maybe an RxJS observable or behavior subject, perhaps called session lover I, which holds the current user's claims. It would probably default to null or some anonymous state.
Right, representing the logged out state initially.
And a function within this service, maybe getSession, would be responsible for making that HTTP request we talked about to the BFX BFuser endpoint to fetch the actual claims.
Only works if the cookie is present.
Right. This fetch only succeeds and returns claims if there's a valid session cookie established by the BFF. If the BFF returns a 401, the auth service interprets this as user is anonymous and updates its internal state accordingly, maybe to null.
And you'd want to be efficient about calling that endpoint, right?
Absolutely. You'd use common patterns in reactive programming, often using RxJS operators like sharePlay1.
Why sharePlay?
It ensures that if multiple parts of your Angular application, different components, maybe simultaneously try to get the session status, the actual HTTP request to the BFF is only fired once by the very first subscriber.
Avoids redundant calls. Everyone gets the same cached result.
Exactly. And this get session call might be structured using something like defer, so it only executes when actually subscribed to, maybe after the initial rendering. And increasingly now, you'd convert that resulting observable into an Angular signal.
Using to signal, maybe.
Yeah, to signal for that efficient reactive state management the signals provide. And crucially, you then define other computed signals based on this primary session signal.
Like what?
Things like is authenticated, is anonymous, maybe username, and even a log URL signal.
And because they're computed signals.
The beauty is they automatically update throughout your entire application whenever the underlying session signal value changes. No manual subscriptions needed.
Very reactive.
So think about your navigation menu component. It simply injects this auth service. In its template, it can reactively check auth service.is authenticated.
And show different things based on that.
Yep. If true, maybe show a link with the auth service.username and a logout link pointing to BFF. If false, just show a simple link pointing to the BFF login endpoint.
That's really quite simple from the Angular components perspective.
It is. That's essentially all the Angular application needs to know about logging in just the location of that BFF login endpoint. And logout is equally simple, just calling the BFS logout URL.
The elegance there is striking. It shows how completely the Angular frontend is abstracted, decoupled from the messy, complex world of authentication protocols and token handling.
All handled by the BFF.
It trusts the BFF implicitly to manage all that heavy lifting. And the result? Cleaner, more modular, easier to maintain, and inherently more secure front-end code. It really simplifies the developer experience for front-end teams immensely.
Okay, let's switch gears now. Flip to the back-end side. Our example uses an ASP.NET Core project for the BFF. Like many modern back-end platforms, it uses things like dependency injection, a middleware pipeline.
Standard back-end stuff.
Right. And as mentioned, developers often choose a specialized library to help. The example uses one called Duende BFF, which is designed specifically to streamline BFF development and handle many security aspects automatically. Though you absolutely could build this functionality yourself.
Sure, but a library handles edge cases, maybe?
Often, yes. Authentication within the BFF itself is typically configured with multiple authentication schemes. You might have a cookie scheme for managing the local session, and maybe an OpenID Connect scheme for integrating with an external IDP later.
So you can switch between them.
Yeah, or use them together. Initially, in the basic setup, you might have only the cookie scheme active. This cookie scheme would be configured so that if an unauthenticated user tries to access a protected resource, it automatically redirects them to a local login path, like account login.
The BFF's own login page.
Correct. At that account login endpoint, maybe a simple username password check happens. If valid, claims are constructed like giving Bob the name Bob and a unique subject ID 1 and a claims identity object is created. Then the framework signs the user in using the cookie scheme.
And that's what creates the session cookie.
That's the step that creates the secure session cookie, yes. And for robust security, that cookie needs careful configuration. The name, for instance, might start with host.
Host prefix. Why?
It's not just a naming convention. It's a signal to the browser. It enforces strict security rules, like the cookie must be secure, must come from the host itself, not a subdomain, and can't have a domain attribute. It helps prevent it from being overwritten by less secure cookies.
Extra browser level protection.
Yep. And it's configured as a same-site cookie, ideally using strict mode, not the more permissive default of lax.
Right, strict for maximum CSRF protection.
Furthermore, a specific BFF middleware, often provided by the library or custom built, is typically plugged into the backend's request processing pipeline. Its main job is to add another layer of defense against CSRF attacks, often using techniques like double submit cookies or checking for specific headers.
Okay, defense in depth.
Then the essential BFF management endpoints, Beloflagon, Belvoyout Buffuser, along with any custom API endpoints you create, like API houses, are added to the application's routing table.
And configured for security.
Yes, these custom API endpoints are specifically configured to require a valid session cookie for authorization. And they're often marked internally as BFF endpoints so that the CSRF protection middleware applies correctly to them.
Got it.
And finally, there's usually a configuration call, like map fallback to file index.html in ASP.NET Core. This is the crucial piece that ensures if no other defined API or BFF route matches an incoming URL, the server defaults to serving the Angular application's main entry point file, the index.html.
And that's the magic that makes both the BFF APIs and the Angular app appear to the browser as if they're coming from the same origin.
Exactly. That's what makes the same-site strict cookies work reliably.
This comprehensive backend setup, it really is the bedrock of the application's security, isn't it? From the deliberate use of specific cookie flags and prefixes like host, to the dedicated CSRF middleware.
Every layer helps.
Every layer is designed to reinforce the security posture in ways that the client-side browser simply cannot match. It creates a truly robust defense-in-depth strategy.
Okay, now, making your Angular development workflow play nicely with this BFF setup requires a little thought, especially during local development. Developers naturally want to keep those great Angular features, like live reloading when they change code.
The fast dev cycle.
Right. Now, some back-end frameworks like ASP.NET Core have special project templates or features to manage, starting both the front-end and back-end together and proxying requests automatically.
Integrated setups.
But if you're using different platforms, maybe a Node.js BFF and the Angular CLI dev server, you might need to start both processes separately. Your BFF runs on one port, your Angular dev server on another.
Okay, common setup, but then you have the same site problem again, right? Different ports mean different origin.
Exactly. Even during development, a reverse proxy is still essential to make same-site cookies work and also to handle any cross-origin resource sharing, CRS issues, between the Angular dev server and the BFF.
So how do you handle that in development? Setup and Jinx locally?
You could, but there's an easier way. The good news is that the Angular CLI has this capability built in. You can configure a proxy right in your Angular project.
Ah, the proxy.conf.json or proxy.conf.js file.
Precisely. You configure it to route specific URL prefixes like BF, maybe count for that local login, or append to your BFF's actual URL and port number.
So the Angular dev server acts as the reverse proxy during development.
Exactly. It intercepts those requests from your Angular app and forwards them to the BFF. This not only solves the same-site cookie problem, but also neatly handles any CORS issues. Because, from the browser's perspective, the request is going to the same origin as the Angular app, the dev server.
That's very convenient for local dev.
It is. Then, of course, in a real production environment, you'd have separate builds of your Angular app and your BFF. You'd deploy them maybe to containers or servers, and then use a dedicated production-grade web server like NGINX or Apache or a cloud load balancer to act as the actual reverse proxy, routing traffic correctly.
Okay, dev proxy, production proxy. Got it.
One more crucial detail, this time back on the Angular side. The application typically includes an HTTP interceptor.
Angular's HTTP interceptors. Useful.
Very. This interceptor usually serves two key purposes in a BFF setup. First, it automatically sets the with credentials flag to true on all outgoing HTTP requests.
Why with credentials?
That flag tells the browser, please include any relevant cookies, like our session cookie, with this request, even if it's technically a cross-origin request, though the proxy makes it same origin. It's essential for sending the session cookie to the BFF.
Okay, make sure the cookie goes along. What's the second purpose?
Second, it often adds a specific custom HTTP header to requests going to the BFF. Something like XCSRF, maybe with a simple value like 1.
A CSRF header, why is that needed if we have same-site cookies?
Good question. Many BFF libraries, including Duende BFF in the example, require this header as an additional layer of CSRF protection, specifically for API endpoints managed by the session. It's part of that double submit cookie or related CSRF mitigation pattern the BFF middleware uses.
Okay, so it's part of the BFF's own CSRF check.
Right, but there's also a beneficial side effect. When a custom HTTP header, like XCSRF, is present on a request initiated by JavaScript, the browser is actually obligated by CORS rules to perform a pre-flight options request first.
Ah, the CORS pre-flight.
Yes. Think of this pre-flight as a quick check. The browser asks the server, hey, is this JavaScript from origin X allowed to make a request with this custom header to you? The server has to explicitly allow it.
So it adds another check.
It adds an extra security layer on top of same-site cookies. It can help block certain types of CSRF attacks or other unwanted cross-origin requests, even in scenarios where the applications might technically be running on the same origin due to the proxy. It's another piece of defense in depth.
That's a great illustration of defense in depth, layering multiple security controls. It also shows how modern development tooling like the Angular CLI proxy and interceptors and production infrastructure like reverse proxies can align perfectly with these core security principles.
Yeah.
It helps make robust protection a standard integrated part of the development lifecycle rather than some bolted-on afterthought.
Absolutely. Okay, so we've got our BFF set up, maybe using local cookie authentication initially. But this is where the real power of the BFF pattern starts to shine.
Expanding beyond basic login.
Exactly. What if you need or prefer centralized authentication using a proper identity provider? Or what if your application needs to securely access other external APIs that are protected by OAuth?
Integrating with the wider ecosystem.
Right. Integrating OAuth or OpenID Connect into your BFF is actually remarkably straightforward once you have the basic BFF structure in place.
Yeah.
And here's the really cool part.
What's that?
You typically don't need to change anything significant in your Angular application.
Really?
Because the Angular app only ever talks to its BFF endpoints, bflogin, bflogout, bfuser, AP. It doesn't know or care how the BFF performs authentication behind the scenes.
Ah, the abstraction holds.
The abstraction holds beautifully. To enable OIDC, you essentially just reconfigure your BFF. In ASP.NET Core terms, you might simply set the default challenge scheme to OpenID Connect instead of cookie.
Telling the BFF to use OIDC for logins.
Yep. This tells your BFF that whenever an unauthenticated user needs to log in or when logout is initiated, it should redirect them to your configured external identity provider, not the local login page.
Okay, so the flow changes slightly.
The flow changes subtly but significantly from the user's perspective. When you run your BFF now and try to log in, instead of seeing the BFF's basic login form, you'll be redirected to the actual login page hosted by your chosen identity provider.
Could be Okta, Microsoft Entra ID, Keycloak.
Any OIDC compliant provider. You'd use your credentials there. Maybe the demo uses Bob or Alice on the IDP.
And the benefits.
The massive benefit here is immediate. You can now instantly leverage all the features of your IDP. Things like external authentication providers, login with Google, login with GitHub, or enabling advanced security features like two-factor authentication, 2FA, maybe even passkeys.
All configured on the IDP side.
Exactly. All configured directly on the IDP with absolutely no changes or even knowledge required within your Angular application itself. It just works.
That's powerful. And the session.
The claims that end up in the BFF's session cookie will now reflect the user's identity as provided and asserted by the trusted identity provider. The BFF library might also add its own useful claims into the session, like a specific logout rule needed for OIDC logout, which often contains a required session ID hint for CSRF protection during logout, and maybe a session expires in value.
Handy for the SPA to know.
Configuring this OIDC connection in your BFF typically involves specifying details like the identity provider's discovery URL or authority address, your application's unique client ID, and that all-important client secret for the secure back-channel token exchange.
The secret the BFF uses.
Right. You also define the response type as code to ensure you're using the authorization code flow. And you specify the scopes you need from the IDP.
Scopes like OpenID, profile.
Exactly. OpenID is essential for getting the identity token. Profile might give you standard claims like name and email. You might request an API scope if you need an access token to call a protected external API, and offline access if you need a refresh token so the BFF can maintain the session even if the user isn't actively using the app.
And the IDP needs to be set up to allow this client and these scopes too.
Of course. The identity provider itself must be configured on its side to recognize your BFF client, trust its redirect URIs, and allow the requested scopes and flows. It's a two-way configuration.
This is really where the BFF architecture demonstrates its value for enterprise-grade applications, isn't it?
I think so.
It acts as that intelligent, secure gateway, enabling complex authentication features like federation with multiple IDPs, robust MFA enforcement, all without burdening the front-end developers or the front-end code itself with any of that complexity.
Keeps it clean.
It centralizes all those critical security concerns in one place, the BFF, which means vastly improved security posture, better scalability, and easier maintenance.
Okay, now remember how we talked about requesting that API scope when setting up OIDC?
Yeah, to get an access token for an external API.
Right. So that means your BFF, after the user logs in via the IDP, now possesses an access token specifically intended for calling some external API.
Held securely by the BFF.
Exactly. So how does your Angular app actually call this external API if the Angular app itself doesn't have and shouldn't have that access token?
The BFF acts as a proxy again.
The solution is precisely that. The VFF acts as a smart proxy for these external API calls. Let's imagine the external API is, say, another ASP.NET application. It would be configured to use standard bearer token authentication.
Expecting an authorization or token header.
Correct. And it would be configured to trust access tokens issued by your same identity provider. It would likely design its own authorization policies, maybe ensuring that incoming access tokens have the correct scope, value, or API scope, and perhaps checking for a valid subject ID claim.
Standard resource server setup.
Yep. Now here's the truly impressive part again.
No change in Angular.
No change needed in your Angular application. Assuming the external API exposes endpoints with the same relative paths as the internal API we might have started with, houses, your Angular app can simply continue calling those API endpoints exactly as before.
It doesn't know the backend changed.
It has no idea the implementation shifted from internal BFF endpoints to proxying external ones. On the BFF side, you just update its configuration slightly. Instead of mapping ape2 to local handlers, you'd use a method provided by your BFF library, maybe something like map remote bendpoint.
Sounds descriptive.
It tells the BFF. For any incoming requests that start with API but don't handle them yourself, instead, forward them to this external API-based URL. And crucially, the library or configuration takes care of automatically attaching the appropriate access token that the BFF holds for the current user before sending the request onwards.
Very seamless.
So when you run this version of the demo, you'd need to start both the external API project and your BFF project. After logging into the IDP, the application's functionality and the data displayed would appear identical to the user. But under the hood, it's now transparently fetching data from that secured external API, facilitated entirely by your BFF.
And what about token lifetimes? Access tokens expire.
Good point. Access tokens usually have short lifetimes, maybe an hour or less. But remember, we requested the offline access scope, which gave the BFF a refresh token.
Yes.
The BFF library will typically handle this automatically. Before proxying a request to the external API, it will check if the current access token is still valid or close to expiring. If needed, it will transparently use the refresh token in another secure backchannel request to the IDP to get a fresh access token.
All handled silently by the BFF.
All handled silently by the BFF, ensuring the Angular app continues to work seamlessly without ever needing to know about token refreshing complexities.
This is a really powerful demonstration of how the BFF architecture not only enhances security, but also dramatically streamlines the process of integrating with protected backend resources, both internal and external.
It simplifies things a lot.
It does, but it raises an important follow-up question. We've talked extensively now about authentication, verifying who the user is, and getting tokens securely via the BFF. But what about the next step? Authorization.
Right.
That is, deciding what the authenticated user is actually allowed to do within the application.
That's a critical distinction, isn't it? We've spent all this time proving who the user is.
That isn't a banshee.
Authentication. Now we need to pivot to authorization, restricting what actions that verified user is permitted to perform, or what specific data they're allowed to see or modify.
Where does that logic live?
So the big question, where should authorization logic be implemented? It's absolutely crucial to understand that while an identity provider issues claims things like roles, group memberships, may be specific permissions, the IDP itself does not enforce these claims within your application.
It just provides the information.
It provides the raw identity information. The actual enforcement of rules based on those claims must occur within all the applications that receive and consume those claims. Meaning, your front-end Angular app, for UI purposes, your BFF for its own endpoints and proxying decisions, and any external APIs that your BFF calls. They all need to perform authorization checks.
Everyone needs to check permissions.
This is a point that simply cannot be overstated. You might be tempted, especially as a front-end developer, to think that just hiding UI elements is enough. Maybe you hide an admin button if the user doesn't have the admin role claim.
Seems logical, right? Hide what they can't use.
It seems logical for user experience, but for security, the answer is a resounding no. That is absolutely not enough.
Why not?
Because, as we keep saying, any content sent to the browser can be inspected and manipulated. Hidden UI elements can easily be revealed using browser developer tools. A determined user could potentially find a way to trigger the underlying action anyway, perhaps by crafting an HTTP request directly.
Bypass the UI check.
Exactly. Therefore, front-end authorization checks, hiding buttons, disabling controls should be considered primarily as enhancements to the user experience. They guide legitimate users, prevent confusion, and make the UI cleaner. They are not definitive security measures.
So where is the definitive security?
The backend or the API must always enforce the definitive security controls. That's your last line of defense, the gatekeeper that cannot be bypassed by manipulating the client-side code.
That's a really common misconception, isn't it? Developers often assume, well, if the button isn't visible, the action can't be taken.
Yeah.
But the browser is effectively an open book in that regard. True security is about restricting access at the source, on the server, regardless of what the user's browser happens to be displaying at the time.
Let's apply this to a simple, concrete example, an add button in our app. It should only be displayed, and the underlying action only allowed if the user's role is admin. In a scenario where your BFF is handling local login, maybe in that account login endpoint, you could explicitly add a role claim with the value admin for a user like Bob when you create his session.
Hard code it for the demo.
Right. If you were using an external OpenID Connect provider, this role claim would ideally come from the IDP itself, maybe based on group membership, provided it was covered by a requested scope in your BFF's OIDC configuration.
Okay, so the claim exists in the session.
So the claim exists in the session data returned by the BFF's BFF user endpoint. In your Angular auth service, you would then add a computed signal, maybe as admin, to specifically extract the value of this role claim from the session data and check if it equals admin.
A Boolean signal. True admin, false otherwise.
Exactly. Then, in your component's HTML template where the add button lives, you could use an Angular directive like ngif and bind it to that authService.asAdmin signal.
So ngif authService.isAdmin on the button.
Precisely. If the signal is true, the button is rendered in the DOM. If false, it's removed.
Okay, that handles the UI part, but you said that's not recommended.
Well, wait. That approach works for hiding the UI element, but directly checking role, admin, or using a signal like isAdmin directly in the component template while functional is generally not recommended for larger applications.
Why not? Seems straightforward.
Because it tends to scatter your specific authorization logic or rules throughout your front-end templates. If the definition of can add a house changes later, maybe it requires admin and another condition, you'd have to find and update it everywhere you use that check.
Leads to maintenance headaches.
Exactly. A much better practice is to centralize these authorization rules within your auth service. So instead of exposing a generic isAdmin signal, create another computed signal with a more semantic name that represents the capability, like can add house. Inside the auth service, the implementation of can add house might currently just check if role equals admin. But the point is, the rule logic, what does it mean to be able to add a house, lives in one central manageable location. The component template just binds to ngif authService.canAddHouse.
Keeps the templates clean and the logic centralized. Nice.
Makes refactoring much easier later. Now, as a quick sidebar, what if you need really fine-grained application-specific authorization data that doesn't make sense to put globally in your IDP?
Like permissions specific only to this one app.
Yeah. A common pattern here is to create a separate, dedicated authorization API.
Yeah.
This API would itself be protected, probably requiring an access token obtained via the BFF.
Yeah.
Your BFF could call this authorization API, maybe passing an application identifier to fetch these more specific permissions for the user, and then perhaps merge them into the session cookie, or provide another BFF endpoint for the Angular app to query them.
So global claims from the IDP, application-specific ones from a dedicated auths API.
It's a way to keep concerns separate. Global identity from the IDP, granular permissions managed closer to the application.
That's solid architectural advice, even just for the front-end part of authorization, while we know the back-end remains the ultimate enforcer of security.
Always.
A well-structured front-end with centralized authorization logic using semantic capability checks significantly improves the user experience, makes the code cleaner, and makes adapting to future authorization requirement changes far less painful.
Definitely helps maintainability. Now, Angular also provides a more powerful built-in mechanism specifically designed to protect entire application routes from unauthorized access.
Root guards.
Exactly. Root guards. These are essentially functions that Angular's router executes before activating a specific route. All the guards associated with the route must return a truthy value, like true or a promise true or observable true, for the navigation to that route to actually proceed.
If any guard returns false, navigation stops.
Navigation stops dead. For example, back in our auth service, we might create another computed signal or a function, maybe can see house details, that again checks for the admin role, or uses our centralized can add house logic, depending on the rule.
Okay.
Then in your main routing configuration file, maybe app.routes.ts, you'd find the route definition for viewing house details, perhaps house.id. you'd add a canActivate property to this route configuration.
Activate.
Right.
Yeah.
And in that array, you'd provide a function that calls your authService.canCHouseDetails method.
So the router calls that function before activating the route.
Precisely. In a demo, if Bob is an admin, the function returns true, the router proceeds, and he sees the house details component. If his role changes and he's no longer an admin, clicking on a house link would result in nothing happening visually. The route guard function returns false, and the router simply refuses to activate that route.
Prevents access at the navigation level.
Exactly. And you can get more complex. CanActivate can be used on parent routes to protect entire sections of your application, ensuring a user is at least authenticated before they can even attempt to load child routes, like for a products area.
Protect the whole section first.
Root guards can also be nested. A parent products route might just require basic authentication, while a specific child route under it, maybe products manage, requires an additional has product management access check via its own CanActivate guard.
Layered checks.
If multiple child routes under a parent share the exact same guard logic, you can use CanActivate child on the parent route. This applies a single check to all potential child route activations. For instance, ensuring has product access applies across all products, subroutes, without repeating the guard on each one.
Convenient.
And here's a particularly powerful one, can match.
Can match. What does that do?
This guard allows Angular's router to decide which route definition to even match in the first place, potentially allowing you to render completely different components for the exact same URL path, based entirely on authorization rules.
Whoa. Example.
Yeah. For instance, for the products path, can match could check the user's permissions. If they're an admin, it might match a route definition that loads product list admin component. If they're just a regular authenticated user, it matches a different route loading product list component. If they're anonymous, it could match yet another route loading product list anonymous component, all for the same product's URL.
That's incredibly flexible for tailoring the UI based on roles.
It is, and route guard functions are also quite flexible themselves. They can accept parameters that give them context about the route being activated, like route parameters or data, or the router's current overall state. This can be useful for more complex guard logic that needs to examine query strings or other parts of the URL.
It's genuinely impressive how these front-end routing mechanisms in Angular can offer such a smooth, integrated user experience. They effectively prevent users from even navigating to or seeing content they're not authorized to access in the first place.
Yeah, it feels very seamless when done well.
And it feels like we have to keep saying this, but it's critical. It's that crucial echo of our earlier point. These front-end guards are primarily user experience enhancements. They are never, ever the sole security control.
The backend must check, too.
Always. They reduce user frustration, they guide users appropriately, but the backend API is where the definitive, unbypassable authorization gates absolutely must reside.
We've certainly taken a real deep dive today, haven't we?
We definitely have. Covered a lot of ground.
From exposing those inherent fundamental vulnerabilities of traditional client-side SPA authentication,
The anti-patterns.
to really championing the robust and now officially recommended Backend For Frontend pattern. You hopefully now have a comprehensive understanding of why your browser simply cannot and should not be trusted with sensitive secrets like access tokens.
Yeah, the BFF is the way.
We've seen how the BFF acts as your application's secure bodyguard, really, adeptly handling everything from those complex OpenID Connect flows and secure token management
to protecting against insidious CSRF attacks using same-site cookies and those strategic reverse proxies we discussed.
Right. And we thoroughly explored how to implement authorization effectively, both on the front end for UX and, crucially, on the back end for actual security, emphasizing again that while your Angular app can brilliantly enhance the user experience with conditional rendering and powerful root guards,
the ultimate non-negotiable security enforcement always resides on your backend. BFF, external APIs, wherever the data or action lives.
Always.
This comprehensive discussion leads to an important final question perhaps for you listening to consider. As the web security landscape inevitably continues to evolve, maybe with new client types beyond browsers, new browser capabilities, or even future challenges like quantum computing impacting cryptography, how might the core principles we've discussed today, particularly those underpinning the BFF pattern, need to adapt to remain relevant?
Good question.
Or what new architectural patterns might eventually arise to continue upholding that fundamental, unchanging need for secrets to reside safely on a trusted server, truly beyond the reach and inherent risks of the client-side environment. What considerations, challenges, or potential evolutions come to mind for you?
Something to definitely mull over. That's all the time we have for this deep dive. Thank you so much for joining us,
Thanks, everyone.
and we'll see you next time.